have, so these are the clocks. Yeah, very strange name. But leptons, we have electrons, muons, tau, tau neutrino, muon neutrino, and electron neutrino. Okay? And only these four actually exist and can live in our universe, in our current universe. We spoke about up, down, and electron. We have the electron neutrino. The electron neutrino is produced by the sun, and it just, you have thousands of, I don't know how many, but I think there's lots of electron neutrino passing through your body every second. Because it's just produced by the sun, and it's just emitted all the way to here. Okay, so these three. So why do they exist? Why only these three exist here? And that's because they have the lowest mass. And that has to do with the fact that our universe is no longer as hot as it used to be. It's much colder than it used to be a million years ago. Okay? So if our universe was actually hotter, then these things, these four particles would actually exist, not these four ones here. And same thing, so if it's even hotter, you get these things here. Maybe there are more at different scales, we don't know, but certainly these 12 particles we have created and we have detected, so we know, we have proof that they do exist. That's for sure.
How does heat stabilize bigger particles?
It doesn't.
More mass.
It doesn't stabilize. It's just the fact that, so if we create, for example, now these things used to exist at the time of the Big Bang. These existed, and also we can create them in our detectors because they need extreme conditions. So if you create, for example, a tau that would come up of your detector, and then just moments after that, it will decay into the muon, and the muon will decay into electron. So they are the same characteristics, just that they're massive. So they are just massive particles. They have the same charge. Just so a muon is a massive electron, and a tau is even a more massive electron. So why do they? It's just all has to do with the E equals mc squared, the theory, where mass and energy is equivalent. So our energy that we have, average energy that we have at the moment, is much lower than it used to be a long time ago. That's why they all decay into the lowest mass that there is. Okay? Maybe if we're colder, maybe there are 4 other ones. Maybe if we're hotter, maybe there are 4 other ones. We don't know, but certainly this is what we know up to now. So you can also see that the scale, as you come up, charge increases. As you go to the right, mass increases. That's why we're talking about this having the lowest mass. But a big question comes when we talk about mass.
Excuse me.
Yeah.
You said they are going to decay. So is it possible to have in a stable conditions this tau, for example? So if you have a really hot place for a longer time, will it be stable or will it anyhow decay?
No, it has to be really hot for it to be.
Yeah.
It's not possible, but yes, it will stay like that.
If it stays at it, okay.
It definitely will stay like that. Yeah.
Another question: when tau decays, for example, where does the rest of the mass go?
Mass converts to energy. Mass converts into energy. So if it has mass,
then how do we see? I mean, can we detect this energy?
You detect it.
The energy is. I mean, the energy goes into energy goes into different kinds of forms of energy. So you don't actually see energy. Energy can be detected, but you see the outcome of energy, which is energy converted into mass. So this is what you see. Okay. So, but back to what I was saying. So the biggest question is mass, and one of the questions is actually mass. Why an electron has mass but no volume? How could something have mass but no volume? Does that actually make sense to any of you? Can something have mass but no volume? Yes? No?
Well, what is mass actually?
Well, this is the question. I mean, but first, before we answer the question, what is mass? But can you, for what you know at the moment,
I mean,
with your understanding, does that actually make sense?
It's a question as there's a vacuum volume, so outside the universe there's a lot of
Vacuum is vacuum. Vacuum has nothing.
So
vacuum is not a particle. Vacuum is just vacuum. It's basically empty space. So it has nothing to do with mass or volume or anything like that. Does it make sense to you? Vacuum is just, it has no energy.
No, of course, it's just a fuzzy terminology. That's it. I mean, and then it's